So we are going to continue the discussion on the factors. I think we are not going to finish them all today, which is a little bit bad, but we will inshallah handle, because we'll have to use the remaining lectures for solving examples, talking about the strength as I promised. So we will now know the stresses, the pitting stress as well as the bending stress, and hopefully we will be able later to understand how do we compare these stresses with some strength, and we judge the safety and of the gear. Now, last class, I remember we stopped here, okay? And it was I think we stopped at the dynamic factor. And let me see, just give me 1 second.
Doctor, chapter 14 will be in the midterm?
No, it is not. I may have told you this, but I was wrong. I checked the email that was sent by the coordinator, and it doesn't involve any material in chapter 14, so only 11 and 13. Okay.
Thank you, Doctor.
Unless you heard something else. For me, I mean, I got the email from the coordinator and it doesn't mention anything about 13, so about 14. Okay. So the dynamic factor, ya shabab, is, if we talk here, we said that the dynamic factor will, you know, was established to include or to consider effects due to the generation of the tutor profile, dynamic vibration, so on. And we said that what AGMA did, or at least we kind of touched on this, is that they established a quality number. And the quality numbers goes from 3 to 7 for most commercial quality gears. And they go from 8 to 12 for high precision quality gears. And I may have told you this or the other section, when we talk about high precision, it means it is something very critical, like something related, impact lives directly, or, significant loss. As I said, if you send a space mission to Mars and then you land a rover there, which happened like 2 weeks ago, you would not expect that the rover will have, commercial quality gears. There is no, I wouldn't believe this. I mean, the whole journey, the whole mission cost you $6-7 billion, and then you go and buy commercial gears from the market. I wouldn't believe this. And if the rover stopped working because you have a problem with the gear, I mean, this is so funny. You understand? But I want you to know the edge over here. So commercial means everything around us in the industry. But of course, there are sensitive places, sensitive industries, and this is where high precision might be used. Now, how can we account for this KV? KV is given as, these two equations, one in feet per minute, the other one in meter per second. And it can be estimated or calculated, by knowing the coefficient A, the exponent B, and the pitch line velocity V. What is A? A is equal to 50 plus 56 multiplied by 1 minus B. So in order to find A, you need to find B. B is finally related to this value. So if you go buy a commercial gear from the market, you would just use a suitable QV. Then from this, you will find B. And by knowing B, you can find A. And by knowing A, you can plug it in there with the velocity, and you will be able to find KV. Now, this is a curve for pitch line velocities, okay, which is in feet per minute, and different quality numbers. So for each quality number, As you change the velocity, you will have different curve. So if you have 4,000 and equality 7, then this is kV. Now, what you should know is, as commented here down in the caption, these endpoints, which are the maximum, are calculated you based on the maximum velocity. And this is the equation for that. So I think this is, again, a very useful equation if you want to bound the solution. What does bound the solution mean? If you are in a design problem and you want to know, like, what is the maximum we're looking for, then this is it. And you know that, okay, I can't go for up more, I can probably go down. So bounding the solution is always very interesting and useful technique in design. So this is why this is very important, I want to tell you. Okay, the next one is the overload factor, KO. The overload factor, KO, basically allows you to consider any kind of effect resulting from an overload, and other than, you know, the transmitted load that you are supplying to through the gear. So if you look here, this table is not numbered. It doesn't have its own, you know, table number. It is part of a big table in the toward the end of the book, the chapter, I mean, which shows you the solution for a general procedure for the entire solution if you want to find sigma C or sigma. And part of that is this table. So I brought it for you over here. Now, what is this table? It tells you that the overload can be basically a function of what is happening to the driven machine compared to the driver, which is the power source. So if you have no idea, it is fair to assume that you have a uniform power source and the driven machine is also performed in a uniform fashion or manner. And for that, this is your K0. So for uniform, we have 0. If you have a uniform power source, but a moderate shock-driven machine, that is possible, where you know that you are supplying the power through a DC motor, you know that you have put a transformer, regulator, whatever, so you ensure that the power source is always uniform. But the operation has moderate shock. Like, for example, if you use that mechanism, the gearing mechanism, to drill, now you cannot guarantee underground or through the wall or whatever that the formation is always uniform. So you may get through a sandy, you know, segment, and then all of a sudden hard rock segment, and this changes the whole mechanism. And there are plenty of things. For example, wind. You can imagine that in places where there are significant wind, you can have this shock because of the wind, but it may be moderate and may be heavy. So if you are the designer and you don't know this, then you better go and ask your client, understand the need, and see basically what are you designing for? What are the possibilities? If you are just an analyst, go and ask him. Tell him, does your application involve shock? Is the shock coming from the source, or is it coming from the driven machine? What causes the shock? And this is where you will understand how do you estimate this. If nothing was mentioned, you can comfortably assume that this is a uniform. Okay? All right. But be careful. Never have a problem of your own. You're designing something, you know everything, and you just because you are ignorant and you did not think about shock, you say, no, I assumed it's uniform. I am the designer. I can assume whatever I want. Of course you can, but you may make the wrong assumption. So be careful with that. Now, the next one is the surface condition factor. Now, the surface condition factor should only be applied to the pitting resistance equation, which is sigma C. Actually, I don't need to highlight this in red in the sense that it will remind you, because if you go and look at equation sigma, not sigma C, you will not find CF in there, which means you don't need it. You understand that? So this is applicable to the pitting, and it makes sense. Pitting is, it's a phenomenon that happens on the surface, and a surface condition factor would probably be related to it. So what are the condition? What surface condition factor depends on? It depends on the surface finish, which can be affected by the cutting, the shaving, the labbing, the grinding, the shot peening. And let me stop here for a few minutes. It's worth it. The shot peening is a very common, well-known surface modification process. And by the way, there is a really, really good chance that when you get a job, by one way or another, you will hear about it, you will get involved with shot peening, or you will even do it yourself or see it with your own eyes. You understand? Now, what is it? It's about supplying a pressurized air and mixing it with tiny little particles. These particles cannot be anything. They are well-selected, specialized particles. Their size, their material has to be designed, selected. But if you assume that the operation is ready, then when you have the gun and you shoot these accelerated tiny little particles, they will fly with high speed, 400 millimeter per second, something like that. And then they will hit the surface of the machine. When they hit the surface, they will make little tiny bumps within the surface. Of course, we taught you in 307 that this is a big no in fatigue, because fatigue is always sensitive to surface roughness. And you would tell me, if I do that, are you crazy? I mean, you're making the surface too rough and you're inducing a little tiny little notches. So how people are doing it in the industry? Well, they do. They do. Why? Because in reality, when you hit the surface with these little high-speed particles, they come at a high speed, and then when they slam in the surface, they generate microplasticity, which means that the surface part, which get hit by this high velocity particle, deformed significantly to the point where it reached to yielding. But this yielding is so localized in a way, it doesn't even penetrate a few microns within the surface. So only few microns, maybe, yeah, a few microns of the surface, 10, 15 will be plasticized. Now, if you have a huge surface below it, which is still elastic, this elastic surface will push on the plastic one, causing it to go under compression. Now, don't get me wrong over here. We always have equilibrium. Otherwise, things will just shatter. So if you have a compression on the surface, how do you balance it? You will have tension somewhere below. You have to. You have to. So the idea goes like this. Having the tension down over a big lump of material, elastic, is no problem. Because if you have a significant compression on the surface, when you load machines, usually the load causes stress on the surface to be higher than down. And in that sense, you are basically producing a field of compression on the surface where most likely crack will start. And by providing that compression, you are actually closing the cracks. So if you tell me, how about the fatigue? You are, increasing the roughness, and this may make the material prone to cracking. Well, yes, that's true. But if you have a rough surface without compressive stresses, you will actually deteriorate fatigue life. But if you have a rough surface with a lot of compressive stresses, you will still be winning. You understand? So I am just telling you this for one reason. I'm not talking about labbing or cutting, because shot peening is a very well-known practical method for enhancing surface strength of and it is widely used because it's very simple, straightforward, and it doesn't involve high temperature. Just put the surface, make sure you wear a mask, and then start shooting it with that gun, and that's it. You understand? Okay, so all of these will affect the surface, and there you go. This is why we have a surface condition factor. However, after this long talk, I am glad to tell you that there is no specific formula by AGMA for CF. So in the end of the day, most of the time we are gonna assume it to be 1. So when should you assume it to be otherwise? Well, if you have a problem, a serious problem, and you have a tabulated or figure or standardized analysis, if you don't have it, again, you need to consult a research or development center or a commercial lab or a university to compute this effect for you. You understand? But as of now, it is 1. Okay? At least you got rid of it. You don't need to worry about it. The next one is the size factor. Now, size always comes into picture, if you notice. I mean, with fatigue, we have a size factor. And here, we have another size factor. And when you read through, it says that size factor reflect the non-uniformity of material property due to size, and it depends on tooth size, diameter of the part, face width, and so on and so on. Now, why is that? I would like you to remember always the fishing rod analogy. If you look at not the fishing rod, the fishing string, the one that you use in the wool, right? It is a little tiny plastic, and I need to be very careful. I am not trying to compare apple to apple over here, because that little tiny string is made from a polymeric material. Polymers doesn't have a grain boundary like metals. So the concept of defects due to, grain boundary, solidification, and hardening, and so on, doesn't apply there. But what I would like you to understand is that this little tiny polymeric material is so strong, really strong. I mean, it is very hard to cut. It's mainly due to the fact that it is small. You understand? So even if you make the same string out of metallic material, that string being like a few hundred micron in diameter is going to have way better strength than the same material making a little bulk or even a tensile specimen. You take a tensile specimen for the same material, you pull it, you find that the strength is 100, 200 megapascal. You go take that tiny little string and you pull it, and you will find that the stress is way higher for failure. Why? Why? Well, you should have heard this a lot, but it is very important, and I want it to be, stuck in your mind. It's very simple. The bigger the size of the material, the more chances to have defect. Is that right? I mean, if defects are inevitable, you can't, unavoidable, you can't escape them. They are always there, especially with metals. Then the smaller the part, the less chances to have defect. This is This is the rule. And that's why whenever you have size, then you need to consider. So for example here, if you want to make a big, you know, gear, ensuring during the manufacturing, during the making, that the property of that gear is uniform. You know, you measure the grain size here or there or there, or it's the same, is very hard, really hard. So that changes the idea of the strength and so on. So what is the factor? Again, AGMA does not have any standardized procedure for detrimental effect. You know what detrimental? The detrimental size effect means the negative effect of the size. So they advise you to use unity, 1. But if there is any reason you think you need to find KS, then there is an estimated procedure. The derivation for it is written in the book in one paragraph. And basically what it is, KS is actually the reciprocal of KB. And KB is the fatigue size factor, if you remember it. Now, if you recall, KB was a function of the diameter or the effective diameter of the shaft or whatever, rectangle. We showed you how to do that. So in the procedure, which is described in the paragraph of the book, it shows you how do we drive the analogy between what is a diameter in KB and what is here a face width, a diametral pitch, and the Y, which is the Lewis factor that I spoke about, that I talked about before. I told you Lewis factor is in section 14.1, and you will hear about it, but we did not cover it. It's an omitted section. So in the end, this is the equation. While the face width is known to us, you know, in terms of gear nomenclature, and the diametral pitch is also known, we need to know what is this Lewis factor. So the Lewis form factor, and just to remind you, Lewis is the person who first established a relation that quantify the effect of bending on, you know, he formulated the bending stress equation for tooth, you know, at a gear. So that Lewis factor, if you look at a schematic of one tooth, if you look, this is the WT, assuming that this is the line of action for WT as a, like, probably the worst scenario here, because, you know, WT will move as the point of contact, and we don't need to talk about that. And assuming that the root over here, A, this is the root of the tooth, then the length between WT to the root is L. And if you know L, and you know the thickness, which is this one, or just the T, this dimension between the two roots, then you square the T, you divide it by 4L, and then you got X. This X is there, this is X. Now, if you take this X, plug it in here, multiply it by 2, multiply it by P, the diametral pitch, divide it by 3, you will find Y. You take that Y, you plug it in here, you have FP, you raise it to the power 0.0535, and then you multiply it by the coefficient 1.192, and then you get an estimate of KS. If you don't need to do this, you can just assume it to be 1, okay? Now, the next one that we are going to talk about is the load distribution factor, which is KM. Now, the load distribution factor comes from the fact that, in general, if you have a shaft, we all understand today that shaft need to sit in 2 bearings like this, preferably, okay? And we know that if we draw in an exaggerated way the deformation of the shaft, then it will become like this. So there, in there, this is the mid-span. The mid-span, when you, if you remember, when we used to estimate the deflection using the deflection equation, and we take the boundary condition. We know that for such a problem, the boundary condition at the midspan, which is x over 2, that the slope here, dy over dx, is equals to 0. Is that right? Now, when you put the gear there, I'm going to draw an exaggerated way. Is that if I draw the gear there, then the gear will sit like this, right? But if I imagine, just imagine, who is it? Anybody was talking, ya shabab? No. Okay, so if you just imagine that if I put the gear in here, then the gear would look like this. Am I right? This is an exaggerated, of course, image, but you can imagine that this is the rule of the load distribution factor. It's due to the fact that we are not mounting the gear in the midspan. This is not always possible. So what should we do? Well, there is AGMA provide this procedure, at least in the book, okay, that we can find a coefficient that will take care of that effect, okay? But we need to make sure that we satisfy 4 conditions over here. All right, what are these 4 conditions? First, this F face width divided by the diameter of the pinion, okay? The pitch diameter of the pinion is less than or equals to 2. That's one condition. The second condition, the gear element, listen to me, the gear element is mounted between 2, so this is the gear over here. And this is the bearing, and this is the bearing. You tell me, yeah, okay, so what? Well, I'm gonna tell you, what about if I have a gear here, a shaft, and then I put a bearing here, I put another bearing here, and then I put the gear here. Who can say no? Nobody. I can do that. Well, as per this procedure, we are not allowed to use it if this is the case, and we are allowed to use it if this is the case. Good. So what else? The face width should not exceed up to 40, and then the contact when loaded across the full width of the narrowest member, which means that the contact between the gear themselves. Now, what is that factor? Now, although we call it Km, but because of these limiting factors, so we don't have a general Km. What we have is a limited Km, load distribution factor, for these 4 conditions. And if we follow these conditions, of course, ya shabab, you should expect that at least for this course, we will only follow these conditions, because I am not going to give you any other conditions which we are not, which we don't have information for. So if we use that, then we will call this factor the load distribution factor CMF. Now, here, as per this textbook, Km is the same as CMF, but for these 4 conditions, okay? And the equation is 1 plus CMC, CPF, CPM, MA, and CA. Funny, right? This is too funny. Now, you will discover that each one of these might be a function of another function, and it just keeps going like this. Now, before I jump into how we find CMC, CPF, and so on, let me tell you one thing, and please listen to me very carefully, because one day you are probably going to do this, okay? There are many students, actually, not only student. One time I was visiting a co-op student, And then the engineer there, who graduated from KFUBM like 15 years ago, was walking with me to the office, and he said, with all due respect, the first thing I told your student when he joined us as a co-op student is to take everything you taught him in KFUBM and throw it in the garbage. Oh, that's a big debate, right? It's a big debate here and everywhere as well. But I'm gonna tell you one thing. I'm not gonna get involved in this discussion about we are right and they are wrong and so on. Okay, just listen. It's very simple answer. If you want to know the answer, there is no such thing as industry without engineering, and there is no engineering without this. Period. The academician, the universities invent the equation, then companies take the equation and convert them into product. The reverse is not. There is no company that invented. Oh, these days we have companies that may invent something. This is true. In Japan, there is an engineer I think he's a PhD, but he's working as an engineer who invented something, ended up getting Nobel Prize for it. This is very well-known story. But these are companies that their sole, purpose is to find solutions, and he ended up inventing something which ended up giving him a Nobel Prize. But the truth is it's always coming from the other way around. So what happened? Why I want to tell you this? What you are seeing right here, I am a guy who would always say I like 307 more than 308 because the 307 is more stresses and I love calculation and so on. But when I see this, I really like 308. This is what I really like about 308 for one single reason. One single reason. I swear, when you get a job in the big companies, Aramco or Sabic, or you deal with them later, you will always know that they have their own standards, Shabab. Engineering standard. Aramco is well known to have one of the most rigorous established industrial standard. They have their own. They use ASTM, but they have even their own, which is more difficult to satisfy. And I heard that it might be so unique, like one of a kind. Now, if you go to their standard, you will see like this to the power 10. You understand? So don't be biased. You love it because it's from Aramco, and you hate it because it's from KFUBM. This is actually like a copy-paste of an engineering standard in a company, because they're not going to talk to you about grain and hardenability and so on. They will tell you as follows. They will tell you, you want to know CMF? Okay, then first tell me, is this a crown or uncrowned teeth? What is a crowned and uncrowned teeth? I actually forgot to add an image, so I'm going to show it to you next class. But if you don't know the answer, just ask the technician, ask the manufacturer, is this crown or uncrowned teeth? If it is uncrowned, then CMC is equals to 1. If it is a crown, then it is 0.8. You move on. Now, I'm going to keep the equation on the top. We just found this related to crown and crown. So the next one is this. The next one is to go and find the face width divided by 10 multiplied by the diameter, the pitch diameter of the pinion. Okay? And then by knowing what is the face, is it less than 1? Use this equation. Is it between 1 and 17? Is it between 17 and 40? And there you go. You have for each one single equation. Now, you should know one thing. First, actually a few things. First, there is a list of the same equations in your textbook for millimeter SI unit. So you should know this. The next thing, there is a note over here. If you calculate this ratio, and this ratio turned out to be less than 0.05, then you must use 0.05, which means this value over here, this ratio, should never be lower than 0.05. If it is lower than 0.05, use 0.05. Understood? And then calculate the rest by knowing what is F, just supply F. Now, when you calculate this CPF, by the way, this is the comment about not using less than 0.05. Now, what is the next thing is CPM. What is CPM? CPM can be 1 or 1.1. How do we know? First, it is related to straddled, mounted pinion. Both of them are straddled. You ask me, what the hell is a straddle? What does it mean? I'm going to show it to you. I'm not going to speak about it. I'm going to show it to you. Don't worry about it. But how do you know which one to go? Well, you have the total distance between the two bearings, and you need to divide it. Actually, this is the total distance between the two bearings. So basically, this is the mid-span. You want to measure the distance between the mid-span and the gear element, which is S1. Then calculate the distance between the two bearings. Take the ratio. If the ratio is less than 0.175, and of course you have a straddled mountain, then use this as 1. If it is greater, then it is 1.1. Now the question, what is a straddle? It's a very simple gearing method. If you recall, just a few slides ago, I told you we are only considering a configuration where the gear element is mounted between two bearings. That's a straddle. So what is the shape of it? This is a real element. I think it's from Ford. I searched and it's from Ford truck. And if you look, interestingly, ya shabab, these are two thrust bearing, okay, tapered, aligned opposite to each other to cancel the axial load out. And then we have the pinion right here. And after that, we have a bearing here. Yeah. So this is the configuration which we are talking about. It's called straddle. If you got bearings right there, and then you have the gear at the end, then you consider this as not straddle. It's actually overhanging, which we are not talking about at all. Shabab, can you then continue the recording? Okay, so this is basically what we were talking about, the straddled and not straddle, and you have seen the images yourself. Let's move on. The slides is coming. So now we go to the next one then. The next one is called the mesh alignment factor, which is CMA, and its CMA is given to you as this. It is an A plus BF multiplied by CF squared. F is the face width. Now, what are A, B, and C? A, B, and C are tabulated for you over here, and they are function of the type of gearing or condition, whether we have an open gearing, we have a commercially closed enclosed unit, or precision enclosed or extra precision enclosed unit. So these are actually available in the figure right here. So this is the open gearing, this is the commercially enclosed, and this is the precision and the extra precision. So you look at the face width, and from the face width, you can find the value for any one of these. Okay, so basically, this is a tabulated a numerical value of the figure 1411. Now, the last thing, which is CE, is related to this. If you have a condition where the gear has been adjusted for assembly, for some condition, you made some adjustment for the assembly, or you have done some labbing for compatibility, you know, and or you did them both. You did assembly modification or adjustment as well as improvement. If you have any sort of modification, anything that falls under this category, you will have CE equals to 0.8. And if there is no special condition, everything is normal, we did not do anything here, then this is for all other conditions, CE is equals to 1. Now, the hardness factor is the next one that we are going to talk about, and probably will not have time to finish it up. But I want to read with me through this slide. It's very important. The pinion generally has a smaller number of teeth than the gear, and consequently, it is subjected to more cycles of contact stress. So there are more contact happening on the pinion than for the gear. And for that, and to make, in both, if it says if both the pinion and the gear are went through some hardening, then a uniform surface strength can be obtained by making the pinion harder than the gear. And since the pinion, so if you want the strength to be equal, because this one is being hit in contact more than the other, then you need to make it harder. And in that case, you will only apply CH, which is the hardening factor for the gear. Look at it, it's used only for the gear. And CH for the pinion is considered to be 1. Now, what is the equation? How do we calculate CH for the gear? It is equal to 1 plus A prime mg minus 1. A prime is some coefficient, some numbers, okay? And we have a hardness ratio. The hardness, this is the perennial hardness that we all know. But as you see, it says the perennial hardness for the pinion divided by the perennial hardness for the gear. Now, this ratio, this equation is valid for a ratio such that HPP divided by HPG for the pinion over the gear is less than or equals to 1.7 and greater than 1.2. So, and you must make sure that these hardnesses are measured using a 10 millimeter ball at a 300 kilogram of load. This specification for the hardness should be provided. You should know what did you use to measure hardness. Now, next, what do we need to do is to find mg. Mg is called the speed ratio, which is, by the way, the famous gear ratio, Ng over Np. Okay. Last thing before I stop. In the case if HPP over HPG is less than 1.2, we said it should be greater than or equal. So what happens if it is less than? Then 1.2, then you should use a 0 over here in this equation. You should use it as 0. If it is greater than 1.7, which is the upper boundary, then use A prime as this. Okay, there are more details about the hardness. We'll talk about them next class, inshallah. So let me stop here. Then I share here my screen. Is it? Take the attendance. So we have. Let me stop also the recording. There is no need